All right, hi everybody. All right, it was another great week of math here at John Muir Middle School, and this past week, we transitioned from solving algebraic equations, where students found that there was only one solution that made that equation true, to now we went into solving algebraic inequalities. So with solving algebraic equalities, the difference is we have more than one solution. And on many occasions, we have infinite solutions actually, which is why we have to do something like this, which is graph. So the first thing we did, actually the prior week, to get ready for this week, is we looked at a little review of how do we graph an algebraic inequality, as well as what is an inequality, what is going on here. So we start off with something like this, and this is something students would have seen in 6th grade math. So in this case, this says x is any number that is less than or equal to 9. Well, if I ask you to name a number that is less than or equal to 9, we could go on forever, which is why there are infinite possibilities. So we have to have some way of communicating our solution to other people. So this is where a graph comes in. So to graph this, we're going to first look at, we want all the numbers that are less than 9. So 9 is down here, so we're going to start at 9. And if we want all the numbers that are less than 9, we're going to simply shade in everything to the left of 9, because these represent all the numbers that are less than 9. And as you can see, we got an arrow also at the end, which tells us that keeps going that direction infinitely, right? All those numbers to the left of 9 are less than 9. But also notice there's a line underneath there, which says that not only can this number be less than 9, but it also can be equal to 9. So we have to have a way of communicating this to our reader. Sorry, kind of sloppy. But we have to have a way of communicating when we get to this 9. Well, does this include 9, or does it go right up to 9? Where does this graph end? So in this case, what we would do is we would put a dot, and we would fill that dot in above the 9 to let the reader know that we are including 9. 9, if I put 9 into this inequality, 9 is equal to 9, so it makes the statement true. So my graph would look like this. If it was just x is less than 9, then my endpoint over here, and this is what we refer to as an endpoint, we would make an open endpoint, which says, okay, we go right up to the 9, but it does not include 9. 9 is not less than 9, so we don't include it. So this is where we first started our work with inequalities, just reviewing some things with inequalities. So then, from there, we went to solving an actual algebraic inequality. And as you can see, this looks very similar to some things that we worked on in our last unit. And so first of all, we look at our inequality and we say, okay, we're looking for all the numbers that we can multiply by -2 that are less than or equal to 9. So again, what numbers in this inequality will make this statement true? Well, again, there are a number of or infinite numbers that will make this statement true. So the first thing we need to do is we need to figure out, well, what is x? Let's define x a little bit further. So to do that, students again quickly found out we're going to solve this the same way we would solve an algebraic equation. So we are trying to get the x all by itself. And in order to do so, we have to get rid of that times -2. So we refer back to our rules. If we want to get rid of something, we do the opposite. So the opposite of times -2 is we're going to divide both sides by -2. And so this is the part where we discovered something. Okay, something happens here when we divide or multiply by a negative. And to show students this, we start off with just something as simple as this. So I just said to students, okay, first of all, do you agree that 3 is greater than 2? Yes, it is. But what happens if I divide by a -1? Well, 3 divided by -1 is -3. 2 divided by -1 is -2. And if I bring down my inequality, this is no longer true. -2 is not less than -3. Believe it or not, -2 is greater than -3. So what we discovered was whenever we divide or multiply by a negative, we need to flip the sign. We need to get the opposite sign, because I reminded students what that negative means. That negative also means opposite. So in this case, we would flip the sign, and once we flip the sign, it's now true again. So as we come back here, notice that we divided by a -2. So because we did that, we're going to again flip the sign. So now instead of x being less than or equal to, it's now greater than or equal to 9 divided by a -2 would be a negative 4.5. Okay? So now I'm going to come back to my graph again. Remember, this is what we just got done doing and reviewing. So now I need to graph all the numbers that are greater than or equal to negative 4.5. So I'm going to come down here. Right here is negative 4.5. So I want all the numbers that are greater than negative 4.5. So we're going to graph everything to the right here, shade in. And then again, I have to ask myself, well, if I put in negative 4.5, does that make the statement true? Is negative 4.5 greater than or equal to negative 4.5? Well, yes, it is. It's equal to it. So I'm going to, once again, shade in my endpoint to communicate to the reader that I want to include negative 4.5. So that was the next step in our progression. And then this led us to the next problem, which again was a little bit more like what we did in our previous unit where we solved multi-step equations. Now we're solving multi-step inequalities. So in this inequality, we have, instead of a one-step inequality, so meaning one step to get the variable by itself, we now have two steps. So now, again, just like we did before, we're trying to isolate the variable, get the variable all by itself. So in order to do so, we're going to get rid of this minus 5. And again, we're going to do the opposite operation. We're going to add 5 to both sides. And that leaves us with negative 2x is less than or equal to 9 plus 5 is going to give me 14. And now I have to get rid of that times negative 2. So this looks a lot like my previous inequality. I'm going to divide. And notice what I'm dividing by again. I'm going to divide by a negative 2, which again tells me, okay, the opposite. I got to reverse that inequality. So instead of less than or equal to, we're going to make that greater than or equal to negative 7. And again, my last step is, here's my negative 7. I want all the numbers that are greater than negative 7. So we're going to shade to the right. And I have to ask myself, if I put in 7, is 7 included? Negative 7. Does negative 7 make this statement true? And yes, it does, because it's equal to. So once again, I'm going to shade in my dot. So these were the inequalities that we spent the majority of the week working on. And they did get a little bit more intense than this. We're a little bit more challenging. We went to multi-step where distributed property came back in, combining like terms. And then the last thing we did is we ended the week, as we talked about in class, this solving inequality stuff is great, but it's not going to really do us anything unless we can solve a real-world problem with it, unless we can actually do something with it, just like we did with algebraic equations. So the last thing that we're doing in this unit that we started on Thursday was we're going to solve some real-world problems, where now students have to write the inequality and then solve it to solve the problem. So they looked at a problem like this. It says Joe's cell phone cost him $21 per month, plus, and notice we have some keywords in here, plus $3 for every gigabyte of data downloaded. What is the limit to the number of gigabytes he can download to stay within his monthly budget of $30? So essentially, we have $30, and we have to make sure that we don't spend any more than that. We're going to stay within our budget. So that means we have to spend less than or equal to $30. So what goes over here then? Well, we already know we're spending $21 a month. Okay, that's right away. Well, then we have this plus $3 per, I'm going to use G to represent gigabytes. So over here is what what I can spend, or what I'm going to spend. And the number of gigabytes depends on, well, my decision of how much data am I going to use. But I know that I can spend less than or equal to 30. I can't go more than 30. More than would mean I'm going to have a greater than sign. So now if you look at my inequality, it looks very similar to the inequality that we just got done practicing solving. But now we can actually solve real problems. So first, I'm going to subtract 21 on both sides. I'm going to get 3G is less than or equal to, in this case, 9. I'm going to divide by 3. Notice I'm dividing by a positive number this time, so I don't need to flip the inequality. And I'm going to come over here for my answer. G, which stands for the number of gigabytes, has to be less than or equal to 3. So this tells me I cannot use more than 3 gigabytes of data, or else I'm going to go over my budget. So again, a practical way of looking at why in the world are we even looking at or solving these algebraic inequalities. So we're going to test this week Tuesday, and then we go full steam ahead where we're going to now bring all this algebraic stuff that we've been working on really all year, we're going to bring it all together into a unit called multiple representations, where we're going to bring back tables, graphs, and equations. Oh my. All right, I'm looking for another great week. Have a good week, everybody. See ya.